Welcome to this lesson. In this lesson, I would like to summarize all the trig functions we have done, which is for sine, cosine, tangent, cotangent, and arc sine, arc cosine, arc tangent, and arc cotangent. And at the end, we're going to have we'll have a discussion about CoSecant and SeCant. Even though we're not going to, but we don't plan to spend a lot of time on doing that due to the limit of time for this course. If there are any questions or there are any issues, then we could set us, if we see time availability for those discussions. And we certainly, I certainly will be very happy to answer any questions you may have on those functions. But anyway, from the beginning of the semester, we introduced the definitional function, okay? And we have talked about what is a one-to-one function, right? One-to-one function. When we talk about one-to-one function, we certainly give the definition, right? We say that function f is one-to-one if whenever the inputs are different, the outputs are different as well. So x sub 1, whoops, wrong place, is not equals to f of x2 okay, whenever the inputs are different. Okay, if we recall that definition, and I think I recommended you guys have those concepts in flashcards. So when I talk about this, you understand what I'm talking about. So also we talk about what is not one-to-one function. Okay, if, right, it's going to be the opposite of that statement, and the opposite of that statement, the opposite of not equal, of course, is equal, right? And the opposite of whenever is for some. For some, x1 is not equals to x2. You can see throughout this weeks, right, from the beginning of the semester, ever since we talk about these concepts, we apply these definitions. So we talk about one-to-one function, and we also talk about increasing function. Right, if you recall those definitions, right, we say function f of x is increasing. Increasing can be on an interval, right? We call it I, right? If, right? A function f of x is an increasing function on an interval if whenever, right? We have a whenever one input x sub 1 is less than the other x sub 2, and their output, okay, you can put in any order you want, grammar wise, I think. Okay, f of x1 is going to be less than f of x2. So their output have the same relationship. Okay. And decreasing function, okay, so all of these, everything stay the same, right, for decreasing function, and the change from increasing to decreasing still on an interval. Whenever x1 is less than x2, whenever the input 1 is less than input 2, the output has a reverse relationship. Now, so that's increasing function, decreasing function. And the next concept we talk about is even function, right? A function is even if f of negative x is equals to f of x for any number, right? In the specified in the domain or interval, right? In interval or domain. Typically, we talk about in domain. It could be on interval too. In calculus, you're going to encounter cases that is in domain, or it could be interval, right? All right, so that's even function and odd function. Okay, for odd function is whenever the inputs are opposite, right? Opposite inputs, right? X1, negative x and x are opposites. Okay, and that's the opposite, that's the input, opposite input, and their output will be opposite as well. How do we express these two are opposite to each other? Well, one is equals to the negative of the other. Okay, so this is for odd function. So we introduced this concept from the very beginning. Okay, I believe it's either week 1 or week 2. And we studied functions, we studied that 8 functions, right? From constant function to linear function, quadratic, cubic, root function, cubic root functions. We follow these concept, right? So we have studied these functions. Okay, so the first piece we studied, the first part we studied, if you look back, right, we studied the constant function. So I'm going to put a little table here. We don't need so many rows. Maybe just, yeah, we studied functions such as f of x is a constant, right? And we studied f of x that is x, right? And we studied function that is equals to x squared, right? And we also studied function that is equals to x raised to the power 3, right? We study those functions. So when we study those functions, right? So let's finish, right? F of x that's equals to absolute value of x. We study those functions, right? And we also studied f of x that is equals to the square root of x. Right? We studied a domain range. They're increasing, decreasing, even, odd, right? We studied all of these properties about these functions. Okay, and the next one is f of x equals to 1 over x, right? We studied all these, this is the first group of study, right? And we studied all of these concepts, 1-to-1, not a 1-to-1, why it's not 1-to-1, increasing function, decreasing function, even, odd, for all of these functions. And we continue that study, right? We continue that study. And then we studied the following functions. Okay, we studied the following functions, which are exponential functions and logarithm functions. Okay, exponential functions and logarithm functions. We studied their domain and range, right? We studied a function, right, which is 2 to the power x, right? And we studied a function which is 3 to the power x, right? And then we studied e to the power x, right? And we also studied that they each have inverse, all right? All of these functions are 1 to 1, right? 2 to the power x, 1 to 1, 3 to the power x, 1 to 1, e to the power x, 1 to 1. We studied their domain range and their inverses. Their inverses are log base 2x, right? And so let me put, I can put it F inverse, right? These are pair by pair, their inverse function to each other, right? And the inverse of 3 to the power x is a base 3 logarithm. And for e to the power x is ln x. So we study all of these functions, right? And for all of these functions, we have studied whether they're 1 to 1, increasing, decreasing, even, odd, right? So finally, we started to study trig functions. So we studied sine, cosine, tangent, cotangent, secant, cosecant, and arc sine, arc cosine, arc tangent, arc cotangent. And of course, we have not studied arc secant, arc cosecant, which we may not have time to do. But you can see we follow the same pattern, right? We follow the same pattern. They are all under these concepts. Under these concepts, we study all of them. We study all of them. Okay, we have studied all of them. So look at sine function, right? So here we're gonna review, right? The rule of trig functions are, it's a set of more complicated rules because we have to build a stage, right? We have to build a stage. And on this stage, we have to specify the 3 pillars. These 3 pillars support that trigonometry. So we talk about standard position, right? Which is the positive direction of x-axis, right? So we have that specified, right? And ARD, angle measurement, positive angle are measured counterclockwise from the standard position. Negative angles are measured clockwise from the standard position. So for all these functions, anytime angles is used as input or output, they are all measured by this angle measurement rule, okay? Whether it's the input for sine, cosine, tangent, cotangent, secant, cosecant, or the output for arc sine, arc cosine, arc tangent, arc cotangent, okay? So I'm gonna put a note here, okay? All the inputs to, okay, sine, cosine, tangent, cotangent, cosecant, secant, all the inputs, okay, all the inputs, A, are measured according to the rule of A, of angle measurement. Angle measurement, right? So this is my note for this one here, right? That's number 1, okay? Number two, we now understand that the output, okay, the outputs for arc sine, right? Arc sine takes ratio, produce angle. Arc cosine take input ratio, produce angle. Arc tangent takes ratio, produces angle. Arc cotangent takes ratio, produces angle. Arc cosecant and arc secant, they're all the same. They take ratio, produces angle. So they produce the output. The output for arc sine, arc sine, right? Arc cosine, arc tan, arc cotangent, right? Etc. Okay. All those outputs are also measured. Okay, they are also measured. They're also measured the same way. Okay, so that's how important the angle measurement is with our understanding. So now we can talk about this because we have studied all of these functions, right? So what I meant here is that in particular, right, all of these angles, right, sine, cosine, so all of these 6 functions, 1, 2, 3, so I'm going to reduce a column. Okay. So sine, cosine, cosine, right? Cosine, tan, cotangent, right? CoSecant and SeCant. All of these, right? They take inputs. They take inputs. Their inputs are angles. And of course they each have their specific domains. And these angles are all followed. They're all measured in this way. They're all measured according to this rule, okay? And they produce ratio of various kinds, okay? We're gonna get to the definition. On the other hand, okay, if we look at the arc functions, right? The arc function, they take a ratio as input, moderation, right? And arc sine, arc cosine, arc tangent, arc cotangent. Arc secant, cosecant, I don't think we're going to talk about it. Okay, they're rarely used. You probably don't even see that button on the calculator. So we're not going to talk about it here. And they produce angle. And these output angles are also measured following the angle measurement from the standard position, positive and negative, okay? I hope that is clear. So with the contact we have studied, you know, that I hope that's very clear. If you have any questions, please don't hesitate to talk to me. All right, reference angle. Okay, reference angle is a different concept. Okay, reference angle is not used for inputs. It's just a reference angle. Okay, reference angles are positive acute angle between terminal and x-axis, and we have used them quite a lot, right? And though now comes the definition. Definition that in our discussion, we know that we set the stage, right? This is a part of the stage set. So A is the angle in standard position, which means we measure the angle from the standard position, either clockwise or counterclockwise. And a point, any point, x, y, on the terminal sides of the angle other than the origin, which guarantees that R is going to be positive. So we have the point, we have x, comma, y. X has a physical presence, that's the red, and y has the physical presence, that's the blue. R is square root of x squared plus y squared. The way we describe R guarantees that R is going to be positive. So we have three quantities described here. And next it comes the definition, which we all know, right? So here comes the definition of sine, right? So I'm going to write down that definition, okay? They are so important. They're so important. Okay, so let me make 6 rows, 1 column. Okay, so each one of these, well, they're all rules of functions. They're all rules and functions. The inputs are angles, right? And they each have their specific domain. So the rule of sine and the rule of cosine, right? The rule of tangent and the rule of cotangent. So all of these are different rules, CoSecant and SeCant. Okay, I hope this will make it very clear to you. And the output for them all, for sine, is going to be y over r, right? It's just these 3 numbers, x, y, r. The 3 numbers is being ratioed in different order, right? X over r, that's for cosine. And tangent is y over x. Cotangent is x over y, right? And cosecant is r over y, and secant is r over x. Okay, so these are the 6 rules, and they're all ratios. 1, 2, 3, 4, 5, 6. 6 rules, 6 functions. So all of these are ratios. Okay, ratio of different sort. So you can see there's 3 numbers, 3 quantities specified in the definition. And just these 3 numbers, we take two and make ratios, right? And that ratio is a rule. So rule number 1, rule number 2, rule number 3, rule number 4, rule number 5, rule number 6. And these 6 rules, each one, for each input, it produces exactly 1 output. So we make 6 functions. So now let's look at sine, right? Let's look at sine. For sine, we studied all those concepts. It's a function, of course. Is it 1-to-1? Is it increasing? Is it decreasing? Is it even? Is it odd? Right? We studied all of these. For sine, we studied. So here, I'm referring to the process. You know, the lessons we talk about how we graph sine, right? The gold color is the arc length, and the blue is the blue numbers on the unit circle. So that's how we make the sine curve. And the purple one here is the arc sine, Okay, so here we have a summary here, right? We did the summary from, we definitely did the summary in those lessons. We discussed sine, arc sine, and the inverse of arc sine, right? Domain, the different forms of writing domain and range, in particular the range for sine. These expressions are so immensely important for you to know what it means, and in the future you are going to use it. Arc sine, and we have all these different forms for domain and range. Okay, we have all these different forms for domain and range. And also at the time we talk about arc sine, after we talk about arc sine, then we talk about composition. When we talk about composition, we want you to remind you of for any function that are inverse to each other, right? For inverse functions, for functions, right? So here I'm coming back here to remind you, right? If f is 1-to-1, right? It has exactly, or has a unique inverse. Okay, and we're going to call that inverse f inverse. Okay, f inverse. It doesn't show the negative one well. Okay, so this is better. It has a unique inverse. And, okay, What is more, and there's a very interesting relationship here. Right here, we have F composite F inverse of X, and that's going to equals to X. This is the composition where this X is from the domain of F inverse. Okay, and the composition in another order. Okay, so F inverse, oops, F inverse composite F is also going to equals to X, provided that this X is from the domain of F, right? These two X's, as we talk about, even though we use the same symbol, but they actually could mean totally different thing, especially in the trig function situation. So X is from the domain of F inverse, and this X is from the domain of F. Okay, so sometimes one could be ratio, the other one is angle, right? So we take this concept, right? And we apply it multiple times. Where did we apply it? We apply it with the, we applied it here. We applied it here, right? We applied it here, right? And we applied here sometimes, right? Because some of these are one-to-one, some of these are not one-to-one, okay? Go back to watch those lessons. And so we, where did that then come from? And we don't need that, okay? And we apply these, this property to these inverse functions to each other, right? We got some very interesting discoveries, and we continue to apply that when we study arc sine and its inverse. We understand arc sine is not the inverse of sine. Arc sine has its own inverse, and that inverse is a small piece of sine, right? So that's how we describe it. X, sine is from a interval from negative pi over 2 to pi over 2. And from the connection with the unit circle, so when arc sine is considered, we basically just chop off second quadrant and third quadrant. And this will be the no-fly zone, right? So we mentioned that. And the same technique is applied to all the other functions, right? Arc cosine, arc tangent, arc cotangent. It's just we truncate different quadrants, okay? With that said and done, because these two are inverse to each other, and we got some shortcut for composition. If you have any questions, then please refer to those lessons, which the title of composition of sine and arc sine. For tangent, for cosine and arc cosine, we've done the same thing again. So we repeat the same theme. For cosine. Okay, this is a cosine curve, and we graph the point. We graph from negative 2 pi to 2 pi, just like we did for sine, from negative 2 pi to 2 pi. We spend many lessons to graph these. And arc cosine, right? So here, the gold color refers to the arc length, and the red number refer to the red numbers, which are cosine ratios from the unit circle, right? I hope this will help. This color connection will help us to see these connections. Now, for cosine, of course, we have arc cosine. Arc cosine is not the inverse function to cosine, right? And we studied, is it 1-to-1? Is it even, odd? Is it increasing, decreasing? We have all of those discussions, right? And we know these two are inverse function to each other, right? So arc cosine's inverse is a piece of cosine from 0 to pi. And as a result, we get a shortcut. We got this shortcut from, hold on. We got this shortcut from this piece, right? We got that from that piece, just like what we did with sine, right? So we apply that property for functions and its inverse repetitively, right? So we applied this piece, right, to arc sine and its inverse, and we also applied this piece to, right, we applied that property to arc cosine and its inverse one more time, right? So we each have a same theme discussions, right? We apply these definitions. So next comes to tangent, right? For tangent, we discussed the domain extensively. In terms of graphing, same theme. The gold color, the horizontal measurement is the input, which are angle, which is the arc length. The purple here is the tangent ratio, y over x, right? So tangent domain is carefully designed, defined, discovered, right? And then we discovered arctangent, right? So we have the details about arctangent, how arctangent is created point by point on those special terminals. And the input, output, right? And arctangent and its inverse, right? So the inverse of arctangent is a piece of tangent. It's a piece of tangent, right? So we discussed that. So once again, we apply that one-to-one function property one more time. We got two other perks, right? These are, you can call them shortcut if you wish. And next we discussed cotangent, of course, cotangent. For cotangent is similar theme, right? Just like for tangent, we discussed, is it one-to-one, is it even, odd? We have discussed all of these properties once again. So we repeated the same theme over and over again. And so here's our cotangent. It's domain and range, right? And its inverse is a piece of cotangent, which is from 0 to pi. It's a vertical asymptotes, horizontal asymptotes for arc cotangent, and the limit on at the corner, right? And when the input approaches negative infinity to positive infinity, and once again, we applied this property, and we got two other perks. So this is a repetitive theme that we have done, right? If we go back to the top, right, for all of these functions, what have we studied? We have studied domain and range for that function. We studied, is it one-to-one, right? If we can find one-to-one pair, what do we do with them? And we studied increasing function, decreasing function, even, odd. So we studied these properties for all of the functions we have discussed so far. Now, two more functions we didn't quite study. Okay, two more functions we didn't quite study. So here we only want to mention their domain and range. So here I'm going to put a domain range summary. Okay, domain range summary for trig functions. Domain range summary, right? These summaries, the domain and range is very much related to the definition, right? Very much related to the definition. So here, I'm going to bring that definition with us. Okay, ARD with us. Okay, so to make my point. Okay, so I'm going to put the definition right here, right? Domain and range. When we look at these functions, right? So for sine, right? The domain, we know it's all real numbers, right? Domain, we know it's all real numbers. So let me put it here. Sine. The domain all real numbers. Range. I'm going to use the one that's, I believe, is the most useful. Okay, from -1 less than equals to sine of A less than equals to 1. Okay, this is the most useful domain range. Okay, for cosine, domain range, same. Different curve. Okay. Tangent. Domain. Okay. Domain. The angle can be any real number, but odd number multiples of pi over 2. Okay, so 2k plus 1 pi over 2. It cannot be odd number multiples of pi over 2. Range, all real numbers. Okay, cotangent. We have domain, the angle cannot be multiples of pi, and the range are the same. So our question is, what is the domain and range for cosecant and secant? Okay, cosecant and secant. Right, so we like to have some discussions. Recall that when we make decisions about these, right? So I'm going to bring the unit circle. Excuse me. I'm going to bring the unit circle with us. In our discussion about domain and range, we use a definition for sure, right? And in particular, we focus on our definition. Sine, cosine, not a problem. All real numbers. For tangent, we have found out whatever the terminal, right, is overlapping with y-axis. So that's the terminal we cannot, those are the angles we cannot be used as input. And for cotangent, it's the same thing, because tangent, right, for tangent is y over x. So when x is 0, right, x cannot be 0, right? So here it tells us x cannot be 0. And therefore, whatever makes x equal 0, that would not be, that will cause, 0 divided, 0 as a denominator. Therefore, we found those terminal. For cotangent, the same thing. Okay, for cotangent, it implies that y cannot be 0. Okay, so anything makes y equal 0. Anything makes y equal 0 in the cotangent case, which are, the multiples of pi. So these two terminals are going to be the problem. And for cosecant and secant is actually the same idea. Okay, so let's look at a cosecant. cosecant basically, the denominator is y, right? Denominator is y. Therefore, y cannot be 0. Y cannot be 0. So what will cause y equals 0, right? So in fact, if you see cotangent and cosecant, they should have the same domain, right? They should have the same domain. Therefore, we know the domain of cosecant is the same as cotangent. Same. Because the way they're defined, okay? Because the way they're defined. So here, you know what I'm going to do? I'm going to just put the definition here so we can see better instead of rolling up and down. Okay, so x over r. So what I wish to show you here is that how to identify and how to determine the domain by yourself. Okay, so cosecant is r over y, right? So y cannot be 0. You can see cotangent and cosecant have the same denominator. So whatever makes the denominator 0, that those terminal has to be out. And for secant is r over x, and therefore x cannot be 0, right? X cannot be 0. And as a result, since x cannot be 0, right? If you look at these expressions, one x cannot be 0. X cannot be 0. So secant has the same domain as tangent. How about range? Range will be an interesting game. Range is an interesting game. Why? Because if you look at a cosecant, right, or secant, it's r over y. So let's talk about the range. Okay, the range, take secant for example. Let's take secant for example, okay? Because secant is used more often. Okay, secant is used more often in calculus classes. Okay, secant is defined as r over x, right? We have decided the domain. Suppose now we perform everything in the domain. Knowing that secant, okay, let me make the fonts just a little bit larger, right? And we know r is square root of x, x squared plus y squared. So here's x, right? You can see from this expression, the numerator is definitively at least the denominator. You guys see that? Okay, because the numerator, okay, notice, okay, note the denominator, okay, the denominator is going to be from algebraic perspective, okay, so follow these calculations I'm going to show you. It's very, very important. Very, very important that you know how to manipulate these algebraically, okay? So what the work I'm showing you here algebraically, I will show you another version of it. So you guys in the future, when you need to decide these things, and you can do it for yourself. Okay, so x squared plus y squared. We know that y squared is always going to be at least 0, right? So this piece is going to be at least if I replace y squared by 0, so this piece is going to be less than equals greater than or equals to x squared, right? Because y squared is at least 0. So I replace y squared by the smallest number possible. So this is true, right? This is true. And now how about the latter? The latter equals to the absolute value of x. We all know that, right? So now we go back to secant. To secant, what do we see? What do we see? The top will be replaced by something smaller. Okay, the denominator stay the same. Okay, the denominator is x, and the numerator is replaced by the smaller. Okay, the smallest possible case for that. So what does this equal to? What does this equal to? Well, it's between -1 and +1, between -1 and +1. So this piece is going to be, so here I should give you the answer, but let's see how I'm going to help you to see it, right? Okay, suppose we understand if x is a positive, right? Suppose if x is a positive, we know x cannot be 0, right? If x is a positive, right? In the domain for sure, in the domain, just x to be positive. Okay, that's fine. X is positive. If x is positive, then this piece is going to be, because the absolute value of x, if x is positive, this is going to be x over x. So that's going to be equals to 1, right? So in this case, we know that secant A, secant of those angles is going to be at least 1. What if x is negative? What if x is negative? If x is negative, secant of A, right? So what do we have here? This guy, okay, is going to be, you know, the absolute value of negative number on less than 0, sorry, less than 0. The absolute value of x, if x is negative, is going to be its opposite. So this is 170. Let me make the fonts larger. Okay, you should see there's a negative x here. So this is a -1. So in that case, secant A could be less than or equals to -1. Let me do it another way. I think this I probably have made it a little bit more complicated, even though this works. Let me do it another way, okay? So what I would do is I'm going to take this piece, right, larger than that, right? We take the absolute value. Wait. Okay, I think this will be simpler. Okay, so I'm going to take the absolute value on both sides. Okay, I'll take the absolute value. This is much easier. Okay. If we take absolute value, so here this piece is going to be absolute value. Okay, so this piece is going to be absolute value. So that equals 1. Okay, so we don't need that. We don't need those other discussions. So in the end, we get secant A is going to be greater than or equals to 1. So that's it. Okay, so the range of a secant A is either going to be less than or equals to -1 or larger than or equals to +1. It's the same, it is the same discussion for cosecant, same discussion, okay? For cosecant, okay, for cosecant, we can do the same discussion similarly, okay? Similarly, okay? So for cosecant, we know that cosecant equals to R over Y, right? So we're going to do the same thing. So we're going to take the absolute value on both sides, right? Before we take that absolute value, so here we have the y here, right? And then we take the absolute value. Okay, we're going to take the absolute value on both sides, and this one take absolute value on both sides, and this will turn out to be, you know, the absolute. The top is always positive, right? We know r is always positive, and here in the denominator is going to be absolute value of y, and this piece, right? Just like what we did here, right? We can do something similar. So note, okay? So note, so this piece is going to be greater than or equals to square root of y squared. Okay, I'm just replacing x squared by it's the smallest it's possible. So this piece is always at least this much. And that is equals to absolute value of y. So now I can replace this piece, the numerator, by a smaller number. So that's going to be absolute value of y and over absolute value of y. Okay, and that equals 1, of course. So we ended up with cosecant of any angle in the domain is going to be at least 1. So that's the range for cosecant. As a result, right, cosecant A is less than equals to -1, or cosecant A is going to be at least 1. Okay, so this is a very algebraic discussion. If you can just spend time to get it, it will be really, really helpful for your future manipulation in algebra classes, in calculus classes. Okay, but I do want to give you another perspective. Okay, which is easier to see, another perspective to see this. Okay, another perspective right here. Okay, knowing the definition, right? Right? Sine definition is the blue, right? Sine of any angle is going to be the blue number. Now you find the reciprocal of all these blue numbers. What do you get? Right? Because cosecant angle is going to be the reciprocal of the blue numbers, because cosecant and sine are reciprocal to each other. So if you see that the reciprocal of √3/2 is going to be, you know, and you just find the reciprocal of all of these numbers, you're going to start to see every one of them is going to be at least 1, right? Or smaller than -1. So let me show you. Okay. By definition, cosecant is r over y, right? R over y. And if I write it this way, if I do just a little bit algebraic manipulation, that's y over r. Okay, I'm kind of giving you all kinds of, you know, possible manipulations as much as possible. Okay, do not be intimidated. If you have any questions, come to my office hours or just message me. I will explain to you. Okay, because sine is a blue number, right? Sine is a blue number. So, and if you see the definition, right? Let me bring the definition to us. I'll try to give you a thorough. Okay, right here. You see sine, I'm just taking the sine. I'm just taking I'm just going to take the sine and the cosecant. How about that? Okay. And I don't need anything in between. Just keep it simple, right? They are reciprocal to each other, right? Y over R, R over Y, right? They're reciprocal to each other. So that's why cosecant, if you want to find those values for cosecant, you're going to have 1 divided by the blue. So now if we make a table, out of this, right? If we make a table out of this, right? You can see, of course, this is just from the special value, what we can see, right? If we make a table about, that makes multiple columns, okay, multiple columns. And over here, I know that sine values, right? Sine of pi over 6. Pi over 6 is half, right? And cosecant of pi over 6 is going to be the reciprocal of half, which is going to be 2, right? 2 over 1. 2 over 1 is 2. So you keep doing this. Right? And you keep doing this for all of these blue numbers. Okay, so I'm going to give you some more examples, right? Sine pi over 4. And it's going to be 1 over root 2. Okay, 1 over root 2. Okay, so how about cosecant pi over 4? Cosecant pi over 4. And that's going to be root 2. Right? So and you keep going. You do sine pi over 3. Pi over 3 is going to be root 3 over 2. Root 3 over 2. Right? Root 3 over 2, then cosecant of pi over 3 is going to be 2 over root 3. You see the reciprocal of it. And each one of these values, as you observe, is going to be at least 1. This is larger than 1, and this is larger than 1, and this is larger than 1. And there are ones that equals to 1 for sure. Okay, for example, sine pi over 2. Pi over 2, right? That equals to 1, right? So cosecant pi over 2 is 1, right? Reciprocal 1 is 1. So if you keep doing this, you're going to have a table. Then that table shows you all the values, right? All of these, of course, now is positive numbers. And then you can work on some negative numbers, right? You can work on some negative numbers. Let's see, sine of 2 pi over 3, right? 2 pi over 3, what does that equal to? That equals to root 3 over 2, right? Root 3 over 2. That's positive numbers, right? So let's do a negative number. Say 7 pi over 6. That's a negative half, right? Negative half. And the cosecant 7 pi over 6 is going to be negative 2, right? That's smaller than negative 1, right? You can see sine of 3 pi over 4, 3 pi over 2, that's a negative 1. Oh, sorry, I erased it. 3 pi over 2 is equals to negative 1. And cosecant 3 pi over 2 is also going to be negative 1. Right? So you keep going. If you look at if you take reciprocal of all of these blue numbers, and you would realize all of them are either, okay, they're either going to be at least one, either they're going to be at least one, which is here, right? So you have a sense about those numbers. You have a sense about those numbers. Okay, so then you will believe, yes, cosecant of any angle is going to be either less than or equal to -1 or greater than or equals to +1. So now I'm going to put in the summary for the range. Remember where we started, right? We started about that table, right? The range for cosecant, right? Okay, hold on. So I'm just going to write it as cosecant of angle is going to be less than or equals to -1, or cosecant of angle is going to be at least equals to 1. And for secant, the same. For secant, the analysis are the same. You just work with those red numbers. You just work with those red numbers. And you just work with those red numbers. You recognize the range for secant is going to be at least, okay, at least 1. The absolute value of secant is at least 1. Okay, I hope this helps. And maybe I will do a separate lecture just on secant, cosecant, but I don't want to burden you guys so much. But I think these information we have summarized here should be sufficient in terms of your, need whatever you need for your calculus classes. Okay, but I will, because in calculus class you do use secant and cosecant from time to time. Not too much, but you still get to use them. So if I have time, I will make another lesson specifically just on cosecant and secant. So that's all for this lesson. I don't want to make it too long, and I'll see you next time. Thank you for watching.